There's homework that was due a week ago and is now due absolutely final last call right now. And that homework was to create a Python program using PyElf tools and Capstone to disassemble some code. And it looks like you all had a pretty easy time of it for the most part, with the exception of following directions, which some of you struggled a little bit with, but that's okay. We got through it. The output should look like what you see there. That's what you would get from which-ls. If you wanted to check your program, which you absolutely should have checked your program, you could, of course, use objdump and compare the results. It's easy stuff to get all the samples you want. All right. No reason to spend too much time on this. I think you all have pretty much gotten this. Error messages. I gave you all the little thing to print error messages. Some of you used it. Some of you didn't. Okay. It's helpful. It's helpful to me if you use it, because it means that the automated checker doesn't reject your code and have to go look at it. But that's okay. Try to do the disassembly in Python. I can't emphasize enough. Python it's one of its big strengths is interaction, and so you absolutely should try this stuff out at the prompt. If it's working for you there, you can look at the history of things you did at the prompt and basically build that into a file. There were some imports I thought you might need, and yeah, I think that's it. So let's go ahead and see if I can pull this up. And this is my solution, which I'll post somewhere on iLearn later on. And there's nothing magical about my solution. It's just the way that I threw this together fresh this time. I've got a document string in the top of it. You should always have doc strings in your comments. It's a really good idea. I have the imports that I gave you, in addition to importing debug and error from my little debug module. Here's a disassemble function, which we'll come back to. And here's a little thing that figures out if you're starting at the prompt, and so it runs main. Here is main. We check for a command line argument and disassemble the text section of the specified file. So I check to see if you've given me at least 2 arguments. I'm sorry, exactly 2 arguments. If you haven't given me exactly 2 arguments, the name of the file, and then the one command line argument, then I give an error and I exit. Right, the return here will go back up and terminate the program. I print out a debug message, so I know what the argument is, and then I call disassemble with arg1. And that's it. That's my super fancy main function. Almost all the work happens up here in my little disassemble function. Again, with the doc string, I try to open the file as a binary. So remember, it's not a text file, which would be the default. If you just open it without this second argument, or you try to open it as a text file, Python will try to decode the stream as whatever the correct platform encoding is. It's probably going to be UTF-8 for most of us, and that's not going to work. So that will not be a good thing. And you probably won't notice it immediately, because sure, it can open it. It can open it as a text stream. That's nothing wrong with that. It's just when we try to decode it as an ELF file that we'll have problems. And so I catch some things. I catch file not found. I catch if it's a directory, and I catch ELF error. I try to locate the text section. And so the way to do that is to go to the ELF file and do get section by name and get the .text section. If there isn't one, well, the file does not contain a .text section. That's an error, and I return. Otherwise, I save the starting address of the text section, and I save the bytes of data that make up the text section. I go and initialize Capstone to disassemble 64-bit x86, and then I point the Capstone disassembler at the data section, and I tell it the initial address. And then think about that for a minute. I can't just point it at data because data is just an array of bytes. There's nothing in there that tells it anything about the address. So I also have to pass the address so that Capstone can correctly disassemble things and populate instructions with address information. And that's important. If I pass the wrong value for the address, I'll get the wrong stuff back. Right? So this is the address associated with the 0th element of the data array. Make sense? This +1 is the address of data 1, etc. So then I just have an iterator over the stuff that's in this. This is a generator, and so it's going to generate instructions for me, probably using something like yield, and I'll just iterate over them. For each one, I print out the address string that I gave you, and then I print out the mnemonic and the op string, and I'm good. I put 2 spaces here, doesn't matter. There's a normalization thing that runs over your output that fixes that, so I have to think about it. And I'm done. That's the entirety of my complicated disassembly function. Super complicated stuff. All right. So tools. Today's tool is the online disassembler. And instead of having a bunch of slides on it, since it's an online thing, I thought I would just go ahead and hop over to it. So here it is. You can just go ahead and hop right in. And you can upload a file from your machine. Let's do that. I'm going to upload. User bin. What I want something we haven't used before. Clang, that's what I want. So I'm going to upload Clang, which is a C compiler. It figures out some stuff. It figures out the architecture information, gives it a base address of 0. You can not change that here, but you can change some of this information, like syntax style. You can make it Intel or AT&T. By default, it's going to be Intel because almost everything in the world by default is the Intel format. You can have suffixes. That's an AT&T thing for the most part. You can set the mode. The default's going to be correct for this. And you can set the data size. We won't do that. And let's go. And time will pass. And we'll wind up here inside a disassembly of it. And just pointing to, in this case, the interp segment. And you can see there's the interpreter, /lib64/ld.linux, so on. So there we go. We're pointing to that. We don't have to be. We can go somewhere else. So let's do that. We can head over here. There's some symbols. And we could look for one like start. Sure enough, there it is. We'll click on start. And here we are in the start function. Now, up at the top, you can see this little stuff. So over here, we see there's different section names. PLT, there's the text, and the places where the executable stuff will be in blue. So for example, the PLT is executable and the text section is executable. Fini and the init, there's a init right there, are executable, but read-only data and so on, those aren't. Down here, if I can get to it, there's an unknown little guy right here with some stuff in it. We may cover that later. So there you go. And here is the start function. And it looks a little different from some of the ones we've looked at, but there's no reason to panic. In fact, let's see, for Clang, I believe we can find a main function. Yep, we can. There's a main function right there. Notice it says unknown main unknown. We can fix that. So we can right click on this, tell it to create a function here, and we can fix this information. So this could be an int for return, and then we'll need an int argc, char pointer argv, char pointer mvp. And after a few seconds, it'll populate. There it goes. And so now we know a little bit more about this. It doesn't populate this information down into here, which would be super nice. But what do you expect? It's for free out there on the web. It does show you control flow. So for example, right here, we have a jump if below. And unlike the very, very common standard in most tools of showing a dashed line, when there's a conditional branch, this just shows you a solid line, which is okay. Then here's a jump, and then here's another jump if equal. And so you can see that kind of information. And you see it's broken it up into a stretch of code here, but not necessarily into basic blocks the way we might like it, right? Here's jump below to this location, but it keeps on pulling this together, just a different way of representing the stuff. It breaks out the targets. So it terminates only at the target. So there you have that. And you can look at the graph. So we pop over here, and hopefully you'll eventually get one. Yeah, so this is too big. Let's go back to our old friend start. That might work a little better. There are some limits on this. There's a limit to what you can display in the graph. There we go. We have one node. It's not a very interesting graph. We'll have to figure a different spot for it. You can upload files that are, I think, up to 2.5 meg in size. After that, it throttles you unless you have a paid account. And the same thing is true for some other things. And you can get yourself a paid account if you want. Let's scroll down here and grab a block and see if we can display the graph for that. There we go. A little bit more interesting result. And so here's the control flow graph for, that contains that little piece of code that we clicked on from the analysis. And you can see it's a pretty involved little control flow graph. You can look at the file in hex. There it is in hex. You can pop over here to sections. I think this is kind of a nice display because it's all colored. And so it'll tell you that this one is allocated. This one gets loaded. This one's read only. This contains code, etc. So there you go. It finds all the strings in there, points them out for you. So here's one. It's up here in this little section of it. Let's pop back over to hex and see if we can get it to scroll to one. There's file info here. It's basic information about the file. If you forget what file you're looking at, it is down here. Clang. So that's the online disassembler. It's a pretty handy little thing. If you don't have access to a fancy tool and you just want to do a disassembly of a file that's not too big, this will take you right into it. You can create a free account if you want, and you can do stuff like add comments so that you can refer to them later on. It's not as fancy as the Ghidra comment system, but again, it's just free out there on the web, which I think is pretty cool. All right. The online disassembler. Let's talk a little bit about sandboxing of code. So there are some tools out there to sandbox code for execution. Shade, Sandboxy is still around. But maybe you don't want your code sandboxed. Maybe you are a malware author and you would prefer that people not figure out what you're doing. Maybe you have intellectual property in there, right? Maybe your code is code that runs on a gaming console and contains a encryption key to talk to the server. You don't want people cheating. So in those cases, you might not want your code sandboxed. So let's talk a little bit about ways in which sandboxing works. So I promised you a discussion of the trap flag, and so now we're going to get to that. The trap flag lives in the flags register. So you can see here's carry, parity. The adjust flag is still there for some reason. The zero flag, the sign flag, and the trap flag right here. So the trap flag causes the processor to have an interrupt after a single instruction executes. It's basically a single stepping mode for the processor. If I set the trap flag and then I jump to an instruction, that instruction will execute, and then the processor will immediately halt and call my signal handler with a sig trap. And you can go and read about this call if you want. It's not the easiest thing in the world to set up, but you can figure it out. I promise. You all are smart enough to figure this out. If you're super motivated to try to create a thing to single step a program, you'll get there. It's just it's a little bit tricky. How do you set the trap flag? It's pretty easy. The way in which it does it is you push the, there's no instruction that's set trap, and there's no instruction that's clear trap. So how do you do that? Well, this is how it works. You go ahead and push the flags onto the stack. You then explicitly OR that bit with a 1. Now the trap flag is set, and then you pop it back into the flags register. So this is the thing at the top of the stack. Same thing for clearing it. But wait, you may say, what about if I set it, then I'm going to execute that instruction in halt? Not quite exactly the way that it works. You'll have to jump to the instruction, and then you'll get your single step. There you go. Trap flag. You can here's some code that I think is kind of funny. This body of code right here, not the stuff around it, but this little piece of code comes from a piece of malware. And the piece of malware wants to check to see if the trap flag is set. And it doesn't want you to know it's checking to see if the trap flag is set. So it tries to evade pattern matchers. So there are patterns that we can look for people doing this kind of stuff, right? If we see this, we know you're checking the trap flag. But this does the same thing. It just does it in a weird way. And I think, as a piece of malware, it's sort of fun to go through it and see what it does. The first thing it does is what it would normally do. You push the flags on the stack. That's how you're going to get them. The other way to get them is you can move the flags into the A register, but I think you only get like the low byte, in which case you won't get the trap flag. There you go. So once we've done this, the flags register contains all the flags, including whatever the trap flag is set to. And the top of the stack also contains all the flag bits. So now it's in 2 places. Then we pop the flags into EDX. So now EDX holds the flag values. We AND EDX with bit 8, and this masks off the trap flag. There you go. And at this point, I could just check to see if it's 0, but I might trip one of the little pattern matches. And so they keep going. They rotate left by 24 bits. And it's a 32-bit register, so bit 8 ends up at the carry. So they rotate this thing all the way off. And if the trap flag was set, it's rotated into the carry, which means that now the carry bit holds a copy of the trap flag. It's kind of a little clever thing to do. Then they rotate right, and they rotate right by 1A. So that's 16 plus 10, which is 26. So 26 bits, they shifted over. Now it's in the position of the 0 flag. Okay. Fine. Then they push flags onto the stack. So the whole flags register goes back onto the stack again. There it is. So it's in flags. Now it's on the stack. EDX contains a bunch of zeros, maybe with a 1 in the position of the 0 flag if the trap flag was set. Great. So then I AND the value on the top of the stack to 0 out bit 6. What? What's going on here? Well, I've zeroed out the 0 flag. So on top of the stack. So this bit mask with this little B here looks like that in binary. And you see there's 1s everywhere except right here where there's a 0 in the position of the 0 flag. So the result is going to be all the original flag settings, but I will have a 0 here no matter what the 0 flag was set to originally. Great. Now I OR this with the value in EDX. So now I started out with this, I OR it with this, and I wind up with whatever the trap flag's value is in the position of the 0 flag. I pop flags off the stack, so it's gone. And now I do a jump 0. Whoops, do a jump 0. So I branch on the 0 flag, which is actually a copy of the trap flag. And if I branch, that means the trap flag was originally set way up here at the top, which means I'm probably being sandboxed or debugged. And I can go off and show you pictures of kittens and puppies. And if I don't branch, then I will encrypt your hard drive and demand a ransom. There you go. Pretty simple stuff. But I thought that was kind of fun to look at. And this may seem like a ridiculous thing to do, but this just avoids all the common patterns that a lot of the malware checking stuff looks for. It's just a weird way of shifting it around and playing with the flags. And I thought it was worth going through for a number of reasons. Is all this documented somewhere? How do you find out if you're being sandboxed? Well, there's a tool for that. There's code, and the code can be found on GitHub, and it's called Paranoid Fish. Paranoid Fish is a demonstration tool that goes and checks to see if someone is trying to trace you. And here's what it looks like when you run it. It's like, well, is the debugger present? No. Okay, fine. Forcing V. Look at that. Traced. We're being traced. Bad stuff's happening. So you can use the code in here to copy into your own code to try to figure out if you're being sandboxed or traced or virtualized or whatever thing you may not want to be happening. And all this brings up the question of how does GDB work? And remember, I did promise you at some point I would come back and tell you how GDB works. GDB does not use a trap flag. Well, parts of it might, but for the most part, it's not going to. GDB uses int3. So int3 is unique because there's a special single byte opcode devoted to int3, and it's this one, CC. And obviously, it's an interrupt instruction, so it triggers an interrupt. Since the instruction is a single byte, whenever the interrupt happens, the instruction pointer RIP is holding a pointer to the next byte immediately after CC. So if you wanted to know where the interrupt happened, you would just subtract 1 from RIP, and you would know the address of the interrupt. And there you go. So we can peek at the program while being debugged, and maybe we'll find out if GDB is actually using that. So here's some code, quite a bit of code. Most of it just deals with printing stuff. I'm not going to go through all of it, but the basics are, this is your pretty normal setting up for a main. Here's the main, usual stuff and the usual stuff. In between, I print the 16 bytes starting at main, so I load the address of main into RDI. How do I do that? Well, I'm not trying to build a position independent executable, but I am saying default rel. So this is like rel main, and it's going to create a relocation, and it's going to go ahead and put everything in there. And the relocation will get resolved. So once main's address is in RDI, which is the usual first argument, I call phex. Phex is a little subroutine that prints the 16 bytes in space-separated hexadecimal starting at the address in RDI. So usual stuff and the usual stuff. I put RDI in RSI, so the stuff I was passed with my first argument goes into the source register. The address of a buffer goes into the destination register. What is that buffer? It's down here. I reserve 49 bytes and call it buffer, and it's in the BSS section, so it's writable. I can't put initialized data here, but I can allocate space. 49 bytes. What is that for? 16 bytes, 2 characters per byte, that's 32, plus a space for each one, so that's 3 times 16, which is 48, plus 1 for a null terminator is 49. There we go. So I do that. I put 16 into RCX. I then go into a loop. I call pbyte. I increment my source index, and I loop back up here. So I just run 16 times, calling pbyte each time. I put a 0 at the location in the buffer pointed to by RDI, which will be the last part of the buffer, so I'll null terminate it. I then load buffer into RDI, which is the first argument for calling putS with respect to the PLT. So most of the actual encoding work happens over here. This long stretch of code actually encodes a byte as 3 characters, 2 hexadecimal digits and a space, and it puts it in the location pointed to by RDI, the destination index. The byte it obtains is from RSI, the source index. Handy to use these registers this way. It just makes sense. So we go and get the contents, we go and get the address of hex, which is this array of hex digits, and we put that in RDX. This is the address of this. If I weren't using an LEF, I used a move, I would go and find the quad word here and stick it in RDX, which is not what I want. I zero out EAX. I then take the byte pointed to by the source index and I put it in AL, which is a single byte. I take AL and I put it in R9B, which is also a single byte. So I have 2 copies of that. And that's good because I'm going to mess one of them up. And so I shift right AL by 4, so I drop off the low nibble. I then go and take RDX, which moves the address of hex. I add RAX to it, which is the high nibble. So it's going to be 0 to 15. It's going to pick the right one in here for it. And I put that in AL. I then take the AL byte and I put it at the location pointed to by the destination index. And I increment the destination index. So I'm pointing to the next slot. It's a good thing I saved this because I'd messed it up. So I move R9B back into AL. I immediately go get the byte pointed to by the source, stick it in AL, do this, do some other stuff here, and repeat the whole process. And really, this is a little bit redundant, but there you go. And it works. So what does this look like when it's run? Let's see if we can find the right place for it. There it is. So let's go ahead and, yep, that's the right thing. So let's make it, and it builds just fine. And when we run it, we get the 16 bytes that should be the bytes at the start of our main function. Let's do this. And so for main. There it is. And I don't have the bytes in it. Boo. Let's try. I forgot I wanted bytes. There we go. And so the bytes are 55, 48, 89, E5, etc. And what I got was 55, 48, 89, E5, etc. So yep, that's working. That's the first 16 bytes at that location. Let's hop into GDB and let's go ahead and break at main. So we've set a breakpoint at main. If we take a look at main, we'll see here's the stuff that happens. If you remember, typically when you run this and you tell it to break at main, it's going to skip this initial piece and break right here at this LEA. And let's display the bytes, which we can do with R. There we go. Really messy display, but there they are, 55, 48, 89, E5, so on. And so we will stop right here with our breakpoint. So let's go ahead and run it. And we're now at the breakpoint for main. If we disassemble it, here's what we get. Let's continue, and we print out the bytes. And so we print out 55, there's 55, 48, there's 48, 89, there's 89, E5, there it is, 48, CC. Right, there we have it. This is where GDB has inserted our breakpoint. That's how it works. When it does this, it gets a sig break, which causes the program interrupt handler to run and lets GDB trap the program and stop. And that's just how that works. And we could patch the bytes ourselves and put a CC in there and cause the same thing to happen, cause int3 to happen. So that's how your breakpoints work in GDB. And so we did that. Basic idea is you go and you grab the byte, you save it somewhere safe, you put a CC in the place, and then you jump to the address to trigger it. And we can do that because GDB is shoving this little CC into the code. But wait, if you're paying close attention, you might wonder how GDB is able to modify the text section, because the text section should be read only, right? Maybe it's loading it with write permissions. Well, we can check that. So if we're in GDB and we're looking at CC and we break it main, we run it and it breaks. We can look at the virtual address where we stopped, and we can go and look for the process. So if we were in GDB, break it main, we run, we stop here. This is the virtual address I get for this one, and it's the same one as that one. That's great. Let's go ahead and do a PSF, and there's a bunch of stuff going on. But in particular, we can see this little shell has a GDB running, and it's debugging this file right here. So this is the process associated with that file, and that's its PID. Great. So when we have that, one of the things you can do with the process PID, it's right here, is you can look at what its memory map looks like, and you can use the proc file system to do that. So we would go to proc the PID and maps. And in case you're not aware of what's in proc, there's a bunch of stuff in there. And these initial numbered folders, these are processes running on your machine. And this gives you access to information in them. So let's paste our little PID in. And actually, before we do that, let me go ahead and let's see what's in there. So there's a whole bunch of different stuff in here. The command lines in here, information about IO limits and so on, all this good stuff. But in particular, there are the maps. So you see right here, we're going to look at the maps. We're going to do the same thing over here. We'll just cat them. And there's how memory is allocated in this little piece of code. And we'll go through memory at a later time. We'll talk about what all this stuff is, but some of it should be pretty obvious, right? Here is my program. There's libc, which got mapped in by the mapped in at some point. The dynamic loader arranged for it to get mapped into my address space here. It's really going to load it into memory once, but because of virtualization, it can be mapped in everywhere. We'll talk about these. Here's the dynamic loader. It's in memory too. Here's my stack, and here's my fast syscall area. Maybe we'll talk about that too. All right. Notice here's my code, and I have 1, 2, 3, 4 read-only segments, and this segment right here, which is writable but not executable. This is my BSS, right? This is where I'm writing the bytes, so it has to be writable. But none of the rest of them are writable. And in particular, this guy, which is almost certainly where my text section lives, because it's executable, is not writable. So how is it that GDB is able to write to it, right? We look at it, we find where that address lives. It lives in this space, and it's not writable. So how does GDB change the bytes? It shouldn't be able to. The memory protection system says you can't write to this segment, and GDB is clearly writing to that segment. So I guess all security is out the window. It does it because GDB had the good fortune of being the thing that started our code running, and it gets to use ptrace. And if you go and do a man for ptrace, you will discover that the ptrace system call provides a means by which one process, the tracer, can observe and control the execution of another process, the tracee, and examine and change memory and registers. Wow, that sounds like a really secure thing to have in my system. I'm so glad it's there. It's primarily used to implement breakpoint debugging, and system call tracing. A tracy gets to be attached to the tracer. Attachment and subsequent commands are per thread, etc. So there you go. And here's how it does it, right? There's a peak text and a peak data. We can read a word at the address in the tracy's memory, returning the word as a result of the call. Linux does not have a separate text and data address space, so those two requests are equivalent. You can look anywhere you want to. Look anywhere you want to. And you can also modify anything you want to, because again, it doesn't have separate spaces. We didn't know. It just lets you look at and modify anything in the program. So again, very, very secure. It's worth knowing. All right. It's not part one, it's part two, but let's talk about semantics. Where we left off last time. Whew. So it would be awesome if there were a nice, complete, and usable and programmable through an API of some kind semantics for the entire x86-64 instruction set. That would be awesome. I would like that. People who do code reverse engineering, they would like that. Everyone would like that. The only problem with that is that there's no such thing. It does not exist. And then there are lots of reasons why it doesn't. One of the obvious reasons is nobody knows what the whole instruction set is, because there are weird undocumented instructions, there are hidden instructions, there are instructions that are model specific. It's kind of a mess. It's even debatable whether Intel knows what everything does, and we kind of suspect that they don't, because of efforts like the Sand Sifter project, which fuzz the chip and find all this stuff in there that's probably unintended. So be great, but there's not. Another thing to worry about is what the word complete means here. It's doing a lot of work. It's saying it's complete, but in what sense is it complete? If I tell you that increments a register, that's some information about it. Does it set flags? And which flags does it set? And do I need to know that? And how much of that information do I need to know? And how long does it take to execute? How many cycles? And that can change. And what are the different conditions under which the number of cycles that increment requires to run take? And all this stuff is semantic information about the instruction. But you can probably get the sense that it is a pretty deep rabbit hole. I mean, does increment immediately write back to the register? Turns out it doesn't. But I mean, these are all things that are worth knowing. And then usable is doing a lot of work in this statement. What is usable? Well, usable by who, and for what purpose, right? So if I say here's your semantics, and I give you an incredibly dense, complicated piece of formal mathematics, it's probably not useful to you, unless that's your thing. Or if I turn around and say, it increments the register, that might be really useful to you, or it might not be. Depends what you're trying to accomplish. So the first sense is, what can we do with the semantics? And the second sense really deals with what representation do we need for the semantics. And you can think about complete in a variety of different senses, right? We care about parallelism. Well, then we need to know when values are stable and how the pipelines work, etc. Right? I don't know if I mentioned write-back buffers, but if I modify memory with an instruction, that may not happen immediately. It may go into a write-back buffer, and in a single-threaded world, I would never notice that happened. But in a multi-threaded world, I can actually get into a case that doesn't make sense given the interleaving of instructions, just because the write-back buffers haven't been cleared yet. So maybe I care about that. If so, I need to have that kind of information. If I don't care about it, I don't need that information. I can throw it away. Do we care about timing? Well, then I need cycle-accurate information about the command. And that can vary, and it varies in a lot of different reasons. We've already seen that pipelining happens. And so it could be that my instruction is already being decoded and may have already executed while I'm doing something else, right? So suppose that I am In my pipeline, I have a memory access instruction followed by an increment. Well, the increment's probably already happened. The memory's taken so long, the processor has already speculatively executed the instruction and probably a few other instructions. And so when the memory completes, then everything else completes. So, how do I measure the timing associated with it? It's not as simple as saying, well, this instruction takes 6 cycles and just adding them up. All right. So there's a variety of different senses in which things can be complete. Representation. What, are you trying to do analysis in some formal way? That can be good because the formal semantics are often composable, and that's great because I can take the semantics for one instruction, it's followed by a second instruction. I can compose those in the sense of composing functions and get the composite function for those two instructions. That's great. Am I trying to emulate or simulate? Then your formal semantics don't help me necessarily because they're in the wrong domain. What I want is something that's operational. I want something I can execute that will actually do the stuff. And the executable semantics may not be great for me in the formal sense because they're typically not composable. Sometimes we can try to have both. Semantics can be represented in a language like Lisp, and they have been. There's a semantics for x86 written in ACL2, which is a fair improver for Lisp, or in standard ML, and they have been. I think Coq is a fair improver that uses standard ML. I'm less familiar with it. And there's an x86 semantics in there. So maybe we can try to get something where there's both some formal representation, but also I can compose them and execute them. So maybe that would work. So let's talk about some of the representations of these things. Conditional concurrent assignments. This is the form of semantics you see over here on the right-hand side, and it's used in the Hyperion tool, which comes out of a company called Affirm Logic. Maybe they're still called Affirm Logic. I think they may have changed their name. So it looks like this. Here's my add with carry, EAX and 17, and it tells me these are the semantics for it. It's conditional concurrent assignment. So it gives me a condition, and the condition right here is always, right? This is what it always does. And here is the concurrent assignment. So EAX is going to get EAX plus 17 plus the Intel carry flag represented as a bit. So that's what it does. And that's what we expect add with carry to do. It's going to set the 0 flag if that thing that we're talking about right here is equal to 0. It's going to set the sign flag if this thing treated as a signed number is less than 0. It's going to, and so on down the line. I'm going to read all these, but there you go. There's helper functions in here. A nice thing about this is that I don't care what order you execute these in. The order that they're executed doesn't matter. There's the initial EAX and the final EAX. So it's kind of like static single assignment. Everything over here on the right-hand side gets computed as a big vector. And then that vector is assigned to everything over here on the left-hand side in one smash. And so I can do the computations in any order I want here and populate that vector. You do this one first, then this one, and so on. It wouldn't matter. And just populate that vector and I'm done. An alternate way of doing it is conditional sequential assignments where the order does matter. Here's what that looks like. This comes from the binary analysis platform that you can find on GitHub. And this is part of the code that was used to win the DARPA Grand Challenge. And it probably looks a lot like this in some ways. And that's probably not a pure coincidence. The people who built this sat on the, let me think for a second, the west side of the Collaborative Innovation Center at Carnegie Mellon on the 4th floor. And the people who built this sat on the east side of the Collaborative Innovation Center at Carnegie Mellon on the 4th floor and talked to each other quite often. So it's probably not too much of a mystery how that happened, but that's okay. And so here again, we see add Q1 and RAX. And so this uses a lot of temporary variables because it's going to do the sequential work, and it's going to need to refer to the original value of RAX sometimes, and sometimes it's going to need to refer to the new value of RAX. So we're going to save the old value of RAX. We're going to add one to it. We're going to set the carry flag if this ends up being less than this. What? Well, that would be overflowed. Right? If I add one to it and get a smaller number, clearly I've overflowed. Overflow flag and all that. You sort of see all these things being set, and there you go. You'll notice that they're using the AT&T syntax here. Add keywords, and they're adding 1 to the register RAX. That's the source destination. Back here, Intel syntax. There you go. And so that's a different way to represent it. And they have different advantages. For different instructions, this may be a cleaner way to represent it. And for some instructions, this may be a cleaner way to represent it, just the way that it is. Lisp. So if you go and get ACL2 from the University of Texas, there's an x86 ISA book. The libraries for ACL2 are called books. The x86 ISA book contains oodles of Lisp. Oodles of Lisp. If you never any Lisp, Lisp is an acronym for lots of irritating silly parentheses. So it's not really. But there you go. And so here we have, we're trying to define a collection of different operations, all of which have basically the same structure. And we start defining the prefixes like rex and the mod rm and the sib byte that are prefixes to these. And then we go into beginning to define all of the semantics of it. And this combines both the disassembly, that's why you have the prefix information, with the semantics, and you get this rather lengthy piece of Lisp code. And that's another way to do it. And the nice advantage, one of the advantages of this is I can run this. This is executable code, and I can run it and get an answer. Another way of representing it is K expressions. If you have the book recommended for the class and you dig into it, you'll find this stuff. You won't find the gory details of how it's represented, but you'll find this library in there being used, the K framework. The K framework is a really neat library, but you should never look at the semantics because it will cause you to go mildly insane. But you can see what's happening here. Here's add Q, and we're adding a 64-bit register and a 64-bit register. And then we begin to pull all this stuff in. And here is how the carry flag and the parity flag and all this stuff gets set. Here's how the registers get set. Lots of stuff in here. Where's the add? It's right there. Whew. All right. And then finally, there is something called the ROSE compiler framework. ROSE, I forget what it stands for, but it's a compiler. So it compiles source in one language into source in another language. And that can be really helpful for maintaining code. I can translate from one language into another language. Well, why not translate from one language into assembly, or translate, that would be useful. And in fact, you can do that. And so in order to make that work, the ROSE compiler framework has to have a semantics that works in that way internal to it. And it looks like C code. And so this is the dispatch that says I'm in group 1, and then dispatch to one of the different instructions that's in group 1, and go and make that instruction and then execute it. And so it spews out into lots and lots and lots of code interprets the bytes and runs it. And that's fine. You can go get the ROSE compiler. It's also open source. Let's pick on one of these. Let's pick on add with carry. This is the D-word version because that's the code I have lying around. I have the code for Hyperion lying around, and it uses it's a 32-bit. The code I have is for 32-bit. So here's the D-word of add with carry. I'm sure they're doing 64-bit by now. Who knows what they're doing? And this is what the semantics of it look like. And so here is the same semantics for increment, which adds 1 to a register. And there's a fun thing to point out here about the semantics, which is to put them side by side. Here is add, and I've gone ahead and substituted 1 in here, rewritten it for 1. And here's the increment. So add 1 to EAX, increment EAX. Those seem like they should be the same thing, and they almost are. They are almost the same thing, except right here. Add modifies the carry. It might set it or clear it. Increment does not change the carry flag at all. Why do I point this out? Does it matter? This is a piece of semantics that surely does not matter. In fact, a lot of debuggers, Ollie debug and others, treat them as if they're the same. It matters, because if I know that your debugger treats these as if they're the same, then, or if you in your brain are thinking they're the same, I can use a trick. I can make sure the carry, let's say, is clear. I can do some math. I can increment something which would set the carry, and then I can branch on the carry. And if I take that branch, it means I'm being emulated. And I have discovered that I'm being emulated. And I will display pictures of kittens and puppies and butterflies. And if it's clear, then I will go ahead and encrypt your hard drive and demand a ransom. This kind of thing is important. So your semantics may have to go all the way down and deal with each of the individual flags and the conditions under which they're set. So again, how complete is it? And for what purpose are you trying to use it? Hyperion and Q and a few others were built specifically to analyze and deal with malware. And so they had to deal with this kind of stuff. If you want to see more about the semantics of this and sort of walk through how you would decode the bytes, you can go here. And this is a great reference if you care about how bytes turn into instructions, and you probably don't, so you may never want to go here. But if you look at bytes, you can then click through this list of bytes, and you can find out what's going on with them and how they get interpreted by the processor and turned into instructions. There you go. Whew. One more type of semantics that I want to bring up, because I think it's really interesting, and that is P-code. So P-code is another way of representing the semantics of instructions. And it's used to represent the semantics of instructions, not just to x86, but for ARM and AVR and PIC and the 68K processor and old ones like 6502. So it's really important. And it's part of Ghidra. This is how Ghidra gets its semantics. So if you open the code in Ghidra, you get the usual display. It looks something like this. And there is a little, what I'm going to call the Jenga button. Some people call it the hamburger button, but it doesn't look like a hamburger to me. It looks like a Jenga tower. If you click on this little guy at the top of your listing, you'll get a little drop down that will let you turn on or turn off features of the listing. Like, I don't want to see the bytes, or maybe I do want to see the bytes, or I don't want to see the addresses, or maybe I do. And one of the things I can turn on is P code. And when I turn it on, the listing now looks like this. So after every instruction, I have this stuff right here. And this is P code. This is the Ghidra semantics language. And there's a reference for it. You can go, if you've downloaded Ghidra, you'll find it in there. Otherwise, you can find it online here. It's not a very complicated language. It's actually really, really simple. And that's great. That means if you have a tool that needs to work with semantics and you can get this out of Ghidra, which is non-trivial, then you can convert this into a form you can use, and you can work with this. So let's pick on one of these. Let's pick on the semantics of increment, because we've been playing with increment. So it seems like that's a fun one to look at. And here's what it looks like. And so I'm incrementing RAX, and I see something about OF, something about RAX, sign flag, zero flag. I don't see the carry flag in here because, again, increment doesn't set the carry. And I have these little guys, int scary, that sounds scary, and int add, and int less, and int equal. What are those things? Well, let's pick on int scary. If I go and look in the documentation for P code, I'll find it here. It's a predefined function. It takes 2 arguments and generates a single output. So here's the semantic statement. They call this the semantic statement. But when you see it in P code, there's no parens. You just see int scary and then the 2 arguments separated by a comma, like you would in NASM for a NASM macro, which I think is not entirely a coincidence for reasons. And so here I've got the overflow flag, and I want to set this if this statement is true. This operation checks for signed addition, overflow, or carry conditions. If the result of adding input 0 and input 1 as signed integers overflows the sides of the var nodes, output is assigned true. Must be the same size, and output must be 1. Okay, so I'm adding 1 to RAX, and so this says check to see if RAX plus this, what is that, is going to cause an overflow. And if it is, set this to 1 or true, otherwise set it to false. Okay, that kind of makes sense, but what is this thing? Well, this tells me the size of the value. In this case, it's 8 bytes, and this is the value. This is an 8-byte 1. And it makes sense because this is an 8-byte register. So I need to add an 8-byte 1 to it because they have to be the same size. All right. There are the 2 arguments. And so like for int equal, we're going to set the 0 flag if RAX is equal to an 8-byte 0. Up here, we had to check if it's RAX plus 1. Then we added 1 to RAX. Now we're checking to see if it is equal to 0. This tells me that these are sequential statements, right? This activates first. This runs, and it changes the value in RAX going forward. So these guys are able to use the value of RAX after the change. But this guy needs to use it before because it needs to check the value to see if it should set the overflow flag before this line runs. All right. So that's your P code. And it's interesting. If you don't know what an instruction does, you can pull this up and take a look at it. Great. So instead of taking a break, let's take a look at the midterm. And here it is. It's up on the iLearn site. You'll find it in the assignments section. And here's what you'll find. It's an open book, open notes exam. Answer questions to the best of your ability, working on your own. You can write code and run it. You can do whatever you want to do, except collaborate. I'm looking for your knowledge on this. Each question is worth 10% of the exam grade. Some questions have multiple parts. All parts have the same weight. So this tells you if something looks super easy to you, just do it. And then if something seems hard, maybe save that till later on and do it. How do you get results back to me? Well, you can handwrite stuff. That's fine. People do that every year. You can scan this, or you can scan it or photograph it. You can put this in another document and type the stuff in. It's up to you. I'm going to print them out and then mark them up and then scan them in myself. If I can't read your handwriting, I can't grade your exam, and I can't go back and ask you for what you meant. So please write legibly if you're going to handwrite it, and please try to use reasonably correct grammar and spelling. This is a rare thing, but I did have one where I could not make out what the heck the student was trying to say, and I couldn't give many points for it because their answer wasn't a sentence. It was just some weird glom of words. So please don't do that. That gives me a headache. I'll try to puzzle out what you mean, but there are limits to my abilities. Okay. Be sure to explicitly state your assumptions. Every year, students take these exams and they just like assume, well, this must be true. So I'm going to assume it's true and not write it down. And here's my answer. And the answer is wrong. And if I'd known this is an assumption they were making, well, maybe I could have handled that differently. But there you go. So please state your assumptions. All right. I don't know why this is in here. This shouldn't be in here. There's no disassembly. Yeah, I know why that's in there. I put it in, I took it out, then I put it in, then I took it out, then I finally decided I'd move it. So now this is near the end. This is now at the end of the exam. Sorry about that. Static analysis attempts to answer questions by examining a program's instructions. Dynamic analysis attempts to answer questions by executing a program's instructions. So examining, executing. Part A, consider a program that consumes an input file and generates a new output file. Which of these techniques, static or dynamic analysis, would you use to determine what the program does when given an empty input file? And tell me why you chose that one. Same thing down here, but which technique would you use to determine if there is any input that would result in an empty output file? And tell me why you chose that. You run the strings program. Remember, that's one we talked about. It just goes and tries to find strings in a file and prints them out. And that's a common thing you would do when you start out analyzing a piece of code. You'd run strings to see what you can find. And you run strings on a file to see what strings are present in the file, if any. Is that static analysis or dynamic analysis? Please justify your choice. There's a little program called Cheat Engine that some of you may be familiar with. It's for hacking video games. I would never hack a video game. You should never hack a video game. But if you did, you might use Cheat Engine. And so you've got it running, and you note that your character's health is at 65. So you pause the game using Cheat Engine, and it has a little tool that scans memory, and you look for 65. And you get hundreds of hits because there are 65s all throughout the memory. So then you resume the game, you pause again when your character's health is now 46, and you tell Cheat Engine to scan for 46s in those previous memory locations, and it finds it in just one single hit. Great. That's probably where your character's health is stored. So you subtract the address offset that's used at runtime. So you can get the offset, the unmoved memory address. Now you can open up the file in the disassembler, and you can look for code that writes to that address. And you can replace that code with no ops. Great. Now your character is invincible. That's what you want. What parts of that task were static analysis, and what parts were dynamic analysis, if any? None of you would ever do that. Subpart E, you open the program in GDB, and you run it until a license key is requested. So it pops up a little box asking for a license key. At that point, you're in GDB, so you pause the program, and you then run to the end of the current function with finish, and you enter a random license so that the program can go on. But when you do finish, it pauses after it returns, and then you start stepping forward until the program issues a failure message, and you figure out where that happens. And you can repeatedly do that, and you can discover precisely where the key checking is occurring, and then you override it with a function that returns success. And most modern key checking things aren't that trivial, but some still are. Ideally, what you would do at that point is you would decrypt something that the program would need, and maybe you can catch the decryption key. I'm not suggesting you do any of this, just speculating. So that's what you do. And the question is, for this task, what parts, if any, were static analysis, and what parts, if any, were dynamic analysis? Just tell me. All right. Isn't it being a very game-centric exam? I don't know if I intended that. You purchased Valve's latest game, which is called 3, and you really enjoy playing it. The game talks with Valve's online servers, like most games do these days, and you'd like to analyze the traffic that's going from your computer back to Valve's servers on your network, right? Makes sense. You own the network. It's talking on your computer, on your network, sending bytes, and you'd like to know what's happening. So you dig around in the program, or you dig around on the web until you discover an embedded encryption key that's used to encrypt the traffic. Using that key, you can then record with Wireshark or something like that, and then later on decode and decrypt that data, and you can see what it looks like. Maybe it's JSON data, and you look at it and you figure out, oh, this is what's happening in the game. This is what it's sent. I see what's going on. So you figure out what this protocol looks like. And so then you write a small program that uses that key to post its own messages to Valve's server without playing the game. So you can post messages saying player achieved or gained this achievement, or the player has obtained this additional in-game money, or the player has found this item in the game, and you can give yourself money and items and so on. I'm not saying people would do this, but I am saying people definitely have done this. And here are the questions. Part A, you don't share your program with anyone else. Are there any ethical concerns about this? And what are they? Right? Is traffic on your network? What do you think about that? Just give me what you think. You do post the program online via GitHub. And people do that too. If you can go and look, and there's plenty of stuff out there to do these kinds of things. What ethical concerns, if any, might there be with doing that? So just think about that. Think about some of the stuff we talked about before in this context, and just tell me what you think. Question 3. Computability theory. Rice's theorem states that all non-trivial semantic properties of programs are, in general, undecidable. A semantic property is a true or false statement about the program's behavior as opposed to its syntax, right? So does a program ever print the number 17? That's clearly a semantic property. It's about the program's behavior. What does it do? Does the program contain the word Fred? I'll just scan the text. That's the syntactic property. It's different. All right. And then the example. For example, print number 17 is a non-trivial semantic property. I picked the same number. A property is decidable if it can be solved by some algorithm. Otherwise, it is undecidable. In other words, is there a physically realizable decision property, a decision process that yields a result? Be careful. Rice's theorem makes a statement about all programs. When you're dealing with a subset of all programs, you have to consider that subset carefully. All right. So with all that in mind, right, decidable means as an algorithm, it may run until the heat death of the universe, but it will, if it runs long enough, it will eventually give you the answer. Great. That's decidable. If there is an algorithm that may or may not give you the answer, then it may run forever. That's not good. Then you can't solve it. And in fact, that's where the halting problem comes in. So part A, you're given two programs, P1 and P2, and these both read an arbitrary long but finite sequence of integers and report the integer result. Well, there are lots of finite numbers, so this could be really long. Without knowing more, is it decidable whether P1 of S is greater than P2 of S for all sequences S? Right? So it's a sequence of numbers, and I just feed it. Let's say I feed them both the sequence 0, and there you go. And then I feed them the sequence 1, and then 0 followed by 0, and then 0 followed by 1, and then -1 followed by 0, and so on. And is it true that and for all the ones I see, P1 of S is greater than P2 of S? Is it decidable? So part B, a little bit different. Consider the same problem from A. Suppose here the sequence is limited to no more than 1 billion 32-bit integers. And the question again is it decidable whether P1 of S is greater than P2 of S for all sequences S? So go in there, tell me if it's decidable, tell me why you think it is or is not decidable, and we'll be good. Question 4. This is questions about the x86 64-bit ISA. Program count is RIP. The instruction of move 21 into RIP will not assemble. you should go try it. The assembler won't take it. Give me instructions that do assemble, and that have the same effect. Give me a set of instructions, 1 instruction, 10 instructions, I don't care. But I want the result of that to be the value 21 being in the register RIP. It's probably not a good thing. It'll probably cause a seg fault, but that's fine. I just want you to tell me how I can do that. The instruction move RIP into RAX will not assemble. Again, try it. Give me a single instruction that does assemble and has the same effect. So the value of RIP here will be the address of the next line. Give me an instruction that has exactly the same effect as this, but it has to be a single instruction. C, give me an instruction that will align the stack pointer on a 16-byte boundary. D, assembly code pushes argument 2 onto the stack, then it pushes argument 1 onto the stack, and then it calls your code. So you can draw that out and see what it looks like. Write code that loads argument 1 into RDI and argument 2 into RSI and returns to the caller. This is code that I've actually seen. This is like the old code that pushes stuff based on the old calling convention when stuff was on the stack. And they write a stub that fixes it for the correct new calling convention, and then they ship it. So I've actually seen this kind of code. It's weird, but just tell me how you would, the instructions that you would write to do this stuff. Give me a single instruction that multiplies the value in RAX by 5 and stores the result in RAX. And I want a single instruction that does that. All right. I'm going to pause here. Are there questions about anything we talked about so far? I'm assuming everyone that has questions is muted, so that's good. Question 5. These questions are about the AMD 64 calling convention. It's in this document. If you go to the end of the document, it's right there on page 8. You're writing well, at least the summary of it is, you're writing a main program that will conform to the AMD 64 calling convention. Your program uses these 4 registers, RAX, RBX, RDX, and R12, which, if any, of these registers should you save on entry and restore on exit. Your program calls a function that conforms to the calling convention. Your program uses the same 4 registers as before, which, if any, of those registers should you save before calling that function and then restore after calling that function. You write a function that conforms to the calling convention. The function takes 9 arguments. How many, if any, of the arguments must be passed to the function on the stack? You write a function that conforms to the calling convention. The function takes 9 arguments. How do you access argument 5? So there you go. Your function takes 9 arguments. You have to get to those arguments somehow. How do you get to argument 5? And E, for 32-bit Linux code, arguments are passed on the stack. For 64-bit Linux code, arguments are passed in registers, maybe some on the stack too. Why? Why? Why is it not the same? Why didn't we just keep doing it on the stack? Why are they in registers? Tell me what you think the reason is. 6, little Indian byte order has the lowest order byte in the lowest address. 2's complement representation in an n-bit field negates the number by subtracting it from 2 to the n. I want you to express the integer 1796 as a 16-bit binary integer using 2's complement representation. And then I want you to express the integer negative 1796 as a 16-bit binary integer, again, using 2's complement representation. So I expect a bit string and a bit string. C, you store the 16-bit 2's complement representation of the number, minus 1796, in little Indian byte order, starting at location 0x4400. What is the decimal value of the byte that you will store at location 4400? D, is 2's complement representation important for understanding a register's contents? Why or why not? And E, is the byte order important for understanding a register's contents? Why or why not? Trying to see if you understand what's going on with these. 7. So for the following, you can answer the program entry point, the entry point of the dynamic loader, the start of the program's main function, or somewhere else. You start a statically linked program without the C runtime. You load a statically linked program without the C runtime into GDB, and you do start I. Where's the instruction pointer right now? You load a statically linked program with the C runtime into GDB and do start I. Where's the instruction pointer? You load a dynamically linked program without the C runtime into GDB and execute start I. Where's the instruction pointer? You load a dynamically linked program with the C runtime into GDB and do start I. Where's your instruction pointer? And you look up the entry point of your statically linked program using readelf. And you'll find that there's an entry point in there from readelf and see what it is. This is not the address of the first instruction that executes when the program is started. Why not? And you can, again, if you can do stuff by running code, do it. All right. So I can run readelf and I can run GDB and I can look at the two addresses. And then my job is to explain why they are different. All right. Consider each of the following cases and determine when the instructions bytes are complete. That is, all bytes are specified and do not need to be changed further. And the answer could be at assembly time, at linkage time, or at runtime. So here's an instruction. Load effective address, and the effective address is the absolute address of message, and load that into RAX. And message is a location in the same section as this instruction. Load effective address, relative message into RAX, messages location in the same section. Again, relative message into RAX, but this time message is a location in a different section of your program. So it could be so this would be, let's say, in the text section, but this down here might be in the data section. Load effective address of the error location into RAX. Error location is in a statically linked library. And then finally, load effective address of RAX, error location. Error location is in a dynamically linked library. In case you're super motivated to care, this comes from the standard C library, and you could grab it with an extern if you were motivated to write some code. Question 9. You write call put s with respect to .plt and a symbol link and run the code. What's that call actually point to? What does the PLT entry point to? What does the GOT entry point to? Who fills in the PLT entry, the assembler, the linker, or the loader? Who fills in the GOT entry, the assembler, the linker, or the loader? Question 10. Write an assembly language function that takes no arguments and returns in EAX 1 if the stack is not aligned on a 16-byte boundary on entry before any instructions execute, and 0 if the stack is aligned on a 16-byte boundary on entry. Then write C code to call your function, link it, and run it. And so, what's your assembly code? What's your C code? Is the stack aligned on entry to your function? That's an easy one. Yes or no? And explain why the stack is or is not aligned on entry. There we go. So here's that mystery line I had originally at the top and then moved down. Subsequent questions are part of this short assembly listing, which sadly broke across the page. That's tragic, but that's the way it is sometimes. This comes out of user bin ls, and you can see there's a little bit of some control flow happening here. So question 11, consider the code in listing 1, and don't forget that I've broken it across the page boundary. Boo. So consider this whole thing. A proper program has a single entry point and exits to a single destination. For every instruction, there is a path from entry to exit that includes that instruction. A structured program is a proper program built from a fixed basis set of primes. Draw the flow graph for this node, this code. And when you have a sequence like this guy right here, move, sub, move, add, test, you can glom that all into a single box, and you can label it like 70. And that'll be clear to me, because that's what I'm suggesting, right? Combine adjacent function nodes in a sequence and label nodes with the last 2 digits of the address at the start of the code for that node. So if I see a 70, I'll know, oh, that must be here. And that's all that stuff. This results in a smaller flow graph. So it's all the check. And then, is it a proper program, and why or why not? Is it a structured program that uses only if then else, do, while, and sequence? Why or why not? Break the code into basic blocks. So you saw an algorithm for basic blocks. Can you do that? Can you break this stuff up into basic blocks? If so, just do that. Not a lot of code, so it should be pretty easy. Consider the code in listing 1. It's that code we just saw above. Rewrite this code in static single assignment form using subscripts. You can assume memory is not modified. Is that true? Yep, memory never appears over here as an L value. Great. 13, consider the code in listing 1 and assume that only RAX is live at the end of the listing. What variables are live at the start of the listing given this information? So figure that out. And if you just write an answer here and it's 100% correct, that's great. But if you don't feel 100% correct in your answer, you might want to show me your work so I can give you partial credit. I can't give you credit for anything I don't see. A variable is syntactically live at point X if its value at point X is used in a later computation. Make sense? If I'm looking at a particular line of code, and I say the value, right before, right after that line is live, because later on I see it being used in a computation. A variable is semantically live at point X if its value at point X affects the behavior of the program. Consider the instruction XOR RAX with itself. Is RAX syntactically live immediately prior to this instruction? So there's your definition. Just apply it to that instruction. You get your answer. You're good. Is RAX semantically live prior to this instruction? Again, there's your definition. Apply it to that instruction. Get your answer. You're good. It is possible for a variable to be syntactically live, but semantically dead at some point X. And we know that because we know that semantic liveness is undecidable. Syntactic liveness is typically decidable. So we would expect something like this. Is it possible for a variable to be semantically live, but syntactically dead? Explain your answer. So that's a thinker. Think about it. Give me your thoughtful answer. You analyze a function that determines that RDI, RSI, and RAX are live at the start of the function. So what does that tell you about the function? Should tell you something. You should grok what I mean by this. Tell me what you think I mean. Is RAX live immediately after this instruction? Explain your answer. So what's going on here? Right here, this. After this instruction runs, can you tell me if RAX is live after that instruction? And explain your answer. I didn't say semantically or syntactically, so, think about it. Give me an answer. Subsequent questions refer to this short listing. This comes out of user bin echo. Question 15. Program slicing is a technique that discards irrelevant information from a program listing to simplify analysis. We wish to know when the branch at 5554, that's the last line here, this jump if equal, when it's taken. Since the branch is taken when RAX is 0, right? Test RAX, jump if equal. No mystery about that. Since we want to know that, slice listing 6 on the value of RAX prior to line 5551. So prior to this line, slice this code up here on the value of RAX. Convert the slice program into static single assignment form. Use back substitution to determine when RAX is 0 and the branch is taken. Assuming that only RAX is live at the end of the listing, what variables are live at the start based on the full listing, which is not very long. Assuming that only RAX is live at the end of the slice listing, what variables are live at the start based on the sliced listing? Okay. Whew. That's all 15 questions. Again, I'm only going to count your 10 best answers. If you answer them all, I'll count your 10 best answers. It just makes more work for me in terms of grading it. Calling conventions here. And if you forget what these instructions do, I've got a list here that gives you a quick explanation of what they do, like load effective address, the effective address of this expression, and store it in the register R, so on. That's it. That is your exam. Are there questions about the exam?
Yes. So you said we could ask you questions about the exam while we were doing it. Does that just relate to clarifications and the like, and not the actual content?
If you ask, you can ask me anything you want to ask me, and I will decide whether I want to answer the question or not. So if you ask me what is the answer to question 5, I'll probably not answer you.
Okay.
But don't be shy. Ask what you want to ask, and I will decide if I feel like answering that or not, and I'll be consistent about it. Sure. This is due on Monday, and there's no homework. I thought about it, realized you may have other classes, what you were thinking, but you may have taken other classes. They might have midterms too. Who knows? I'm giving you a midterm. I should give you the midterm and not bother with the homework. It's a kind of a bad time to quit the homework, but I think it's better to not overload you with stuff right now. So exams due Monday.
Thank you.
There's no homework.
Oh yes, thank you for not making us do homework and a midterm.
Yeah, I was like, that's a dumb thing. Why did I say that? I shouldn't do that. So, all right. And when you have questions, and you'll have questions, email me, and I'll try to keep checking my email and get back to you. There you go. Midterm is yours. Have at it. Take home, open notes, no collaboration, 8 a.m. Monday, 7 March. The whole point is to figure out if you understand what we've been talking about. So these are all trying to test your understanding. The homework was practical. The midterm is supposed to be theoretical. 15 questions, best 10 answers. And you'll find, and it's almost, I think the midterm ended up almost being in the order that we covered stuff in lectures. So that may help. Next time, we will have the midterm due, but we'll also talk about slicing and program semantics. So we talked about slicing. Today, we talked about program semantics. We'll bring that back together next time, and we'll slice on semantics.